L'Hopital's rule is named after a French mathematician named L'Hopital. He was a contemporary of Newton and Leibniz. Now, he was younger than they were, but died before, I think, either of them. So, but, lived at essentially the same time. So L'Hopital, when he was doing mathematics, that's when calculus was first coming out. And of course, in the 16th, 17th century time period, information was not as easy to come by as it is these days, right? So L'Hopital's biggest claim to fame isn't necessarily his new research in mathematics. His biggest claim to fame is actually that he wrote a really good calculus textbook, probably the first one, at least the first one in Europe. And so L'Hopital's rule has his name on it, but it's likely that he didn't come up with it. Most of the stuff in his textbook was actually done by one of the Bernoulli brothers. He had paid him for it. He gave him like an annual salary and said, any new math you come up with, just send my way. And he shoved it all in this book, and Bernoulli got mad about that later. But I mean, he got some credit for it, and some money. But there you go. So let's go ahead and look at L'Hopital's rule. The thing that is going to be key before we get into what L'Hopital's rule is to know what it does for us. This is a new way to find limits. We couldn't do this back in chapter 2 because it requires us to do derivatives in order to find the limits. So we're kind of coming full circle. We've first talked about limits. Limits gave us access to being able to build a derivative, and now we're going to use those derivatives to give us more power and leverage over limits. So this is a powerful tool, but we have to be very careful about it. In particular, this rule or theorem works for limits that look like either 0 over 0 or infinity over infinity. So this isn't going to be something that's set up to work with just any limit that we run across right away. But as we'll see in some of the examples, sometimes we can force a limit to kind of fit one of these two forms. Before we get into this rule itself, what I want to do is talk about indeterminate forms. Okay, and so what this is when we try to plug into limits, when we try direct substitution, often we get some mess of stuff, and it may involve infinities and zeros and stuff. And what I want to do is outline two different categories for what that looks like. So when we plug into a limit, we may get something called an indeterminate form, or we might not. Okay, so first let me look at examples of things that are not indeterminate forms. If I plug into a limit and I get something like 0 over infinity, the numerator is pulling me towards 0. The denominator, if I think of like 1 over a big number, is pulling me towards 0. So both of these are pulling me in the same direction. So if I end up with a limit that looks like 0 over infinity, I say, oh, okay, that's just going to give me a 0. Okay, so that I don't have to worry about that. If I have the other way, infinity over 0, and the numerator, the infinity, is pulling me towards infinity, 1 over 0 is usually an indicator for an infinite limit. So both numerator and denominator are pulling this whole quotient towards infinity. So we don't need to do further investigation. Like, we know what's going on there. If I have something like infinity times infinity, one big number times another big number is going to give me an even bigger number, so I'm just going to get infinity. Or infinity plus infinity, right? That's going to give me infinity. Or if I have like a negative infinity minus infinity, right? That's going to give me a negative infinity. So these are examples not of arithmetic. We don't actually add infinities. What we're doing is we're saying I'm adding functions, and the functions I'm adding are getting bigger and bigger. Okay, so they look like infinity. Okay, these are things that we know what's going on. Indeterminate forms are things where we don't know what's going on. So our classic examples are going to be 0 over 0 and infinity over infinity. When we saw these examples back in chapter 2 when we were doing limits, this indicated do more work because we don't know what's going on. Some other examples that we could get could be something like infinity minus infinity, right? So if the first function is getting bigger faster than the second one, when I subtract, I still might be left with a big thing, so it still might end up going to infinity. Or if the second one is getting bigger faster than the first, then the part I'm subtracting, will be bigger, and when I subtract, I'll end up with a negative, maybe negative infinity. Or maybe they're close, and I'll get something like 0. Or maybe the first one is just a little bit bigger, so I'll get like 8. Okay, So anything is really possible when we're subtracting like that. So that's why it's an indeterminate form. Okay, some other ones that are indeterminate would be something like infinity times 0, right? Normally anything times 0 is 0. But what we're looking at here, remember, is not arithmetic. We're looking at when I'm plugging into functions and a limit. So I don't actually have a real infinity, and we don't actually have a real 0. We have a function going towards infinity times another function going towards 0. So one's getting bigger, one's getting smaller, and when I multiply them, I don't know where I end up, right? It depends on which one's going towards its target faster. Similarly, if we get something like 0 to the power of 0, infinity to the power of 0, or 1 to the power of infinity, right? In all of these cases, anything is really possible. It just depends on which function is heading towards its target faster. So what's going to be important is to recognize that in all of these indeterminate forms, we may want to use L'Hopital's rule, but in order to actually use L'Hopital's rule, it has to be one of these first two for it to actually work. Okay, so these are the ones that L'Hopital's rule actually works on. And so, as we'll see in some of our examples, what we do sometimes is we force L'Hopital's rule to fit, right, by changing the function. Or not changing it, but by rewriting it. Okay. Let's look at what L'Hopital's rule actually says. Here's L'Hopital's rule. Suppose that I have two functions. Okay, I want my two functions to be differentiable, at least near this value of a, with either the limit as x approaches a of f of x is 0, and also the same for g, or they're both infinite. And it doesn't really matter which infinity we have, as long as they're both infinite. Okay, so these are our conditions. Then the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f prime of x over g prime of x. So I want to make a couple of comments before we look at an example. First of all, my conditions are talking about what's going on with the limit. Typically, we think of a limit of a single function. What we're doing here is we're really emphasizing a numerator and denominator as being separate functions. Okay, but I need that they're either both 0 or they're both infinite. So we need 0 over 0 or infinity over infinity for this theorem to work. The next remark that's very important is I'm thinking about f and g as being their own separate functions. So the limit of this quotient f over g is equal to this limit of this quotient f prime over g prime. I'm not differentiating the quotient, so that's why we don't use the quotient rule. Okay, so this is very confusing because in chapter 3, when we saw a quotient and we had a derivative, we said you have to use the quotient rule or it's wrong. And now we're saying don't use the quotient rule. So we have to be careful. We have to be aware enough of what's going on and say, okay, I'm not just taking a derivative. That's not how L'Hopital's rule works. What we're doing is we're saying if the numerator and denominator are both going to 0, right? That's what we were talking about up here. They're both going to 0. Then what we're doing is we're really saying which one is going to 0 faster. If the top is going to 0 much faster than the bottom, then I'm going to get these really small numbers, and I'm dividing by something small, but not very small. So as the top goes to 0 really fast, the bottom is kind of taking a lazy approach to 0, then I'm going to get the whole thing is going to go to 0. If, on the other hand, the bottom is going to 0 much faster than the top, then as I divide by these really tiny numbers, even if I start with a small number, it's going to make it much larger. Okay, so if the bottom is getting really, really close to 0 and the top is getting there but slowly, then this whole thing might blow up and I might get infinity. Or the two might be both going to 0 at close to the same speed, and then I might get something like 1 or 2, right? Some finite number. Okay, so we're not taking a derivative of the function. What we're doing is we're treating the numerator and denominator as their own separate functions and looking at how fast are they actually moving. That's kind of the rough idea here. All right, let's go ahead and look at some examples. So let's suppose I have the limit as x approaches 1 of the natural log of x over x minus 1. In chapter 2, I said we should start every limit by trying direct substitution. And when we try direct substitution, it generally won't work, but it'll give us an idea of what's going on. So when I try direct substitution, we get ln of 1 over 1 minus 1. ln of 1 is 0, 1 minus 1 is 0. When I get 0 over 0, I know that direct substitution doesn't work, but I can see that it's in the correct form for L'Hopital's rule. When I work out a limit, what I typically do when I follow my chain of equals, if I'm not going to actually write my next steps next to it, sometimes I use a little bit of a shorthand, and I'll say, like, I'm going to use L'Hopital's rule here to indicate that this limit is equal to this next one, but I've done this rule to get there. So this isn't official math notation, but what this is a good way to be able to follow my own work. So I know, okay, in this step I'm doing L'Hopital's rule. I'm not just, writing down random stuff. So L'Hopital's rule says treat the numerator and denominator as separate functions and differentiate them. So the derivative of ln of x is 1 over x, and the derivative of x minus 1 is 1 minus 0. One of the things that you might notice here is that L'Hopital's rule doesn't solve your problem because you still have a new limit. Okay, so maybe I'll add that as like a third remark. You're never done after doing L'Hopital's rule. Okay, we still have a limit that we have to evaluate. So what I'm going to do is to rewrite this. 1 minus 0 is 1, so I can just write this as 1 over x. And now I'm going to do direct substitution. So maybe as my notes, I'll put like ds for direct substitution to indicate, okay, that's how I'm getting this next step. I plug in 1 and I just get 1. Okay. So the original limit as x approaches 1 of ln of x over x minus 1 is just equal to 1. Let's look at another example. The limit as x goes to infinity of natural log of x over x. So once again, I'm going to try direct substitution, and I get ln of infinity over infinity. And I have to figure out what the heck is going on with ln of infinity. And one of the ways that you can, think about functions is if you imagine what the graph looks like. Okay, there's a graph of y equals ln of x. And as x gets bigger and bigger, as I plug in things going towards infinity, the y values are also going up towards infinity. This is just like having infinity over infinity, which just like before, that means that I can't do direct substitution, but it means that I can do L'Hopital's rule. Using L'Hopital's rule, this is equal to the limit as x goes to infinity of 1 over x divided by 1. And when I take the limit as x goes to infinity of 1 over x, if I remember back from section 4.5 when we were looking at horizontal asymptotes and graphing, we said, oh, as x goes to infinity, 1 over x goes to 0. So the limit as x goes to infinity of natural log of x over x is 0. Okay, let's look at another example. So here the limit's going to go, x is going to go to negative infinity. We're going to have an x squared in the numerator and e to the negative x in the denominator. The first thing I want to do, as always, is to try direct substitution. So I'm going to have a negative infinity squared in the numerator and e to the opposite of negative infinity in the denominator. All right, so let's see if we can figure that out. When I take a negative and square it, I get a positive. So I have a positive infinity in the numerator. In the denominator, the opposite of negative infinity is infinity. And just like with the exponential function, if I think about the graph of e to the x, as my x values get large, my y values get large. So e to the infinity is like going to infinity. So we have an infinity over infinity case, so we're going to use L'Hopital's rule. So this is equal to the limit as x goes to negative infinity of 2x when I differentiate the top. And in the bottom, I'm going to use the chain rule. So e to some function, when I differentiate, I get e to that same function times the derivative of the inside function. And the derivative of negative x is negative 1. All right, so now let's try direct substitution. When I try direct substitution here, I'm going to get 2 times negative infinity on the top, e to the opposite of negative infinity, the negative 1 out in front on the bottom. So 2 times negative infinity is negative infinity. This is e to the infinity, which is infinity, but a negative out front. And I have an infinity over infinity again. So we're going to use L'Hopital's rule again. Okay, so I'm using L'Hopital's rule again, but I think that I'm making progress. Before I use L'Hopital's rule, I want to take a step to simplify anything that simplifies. Now, in this case, I don't think anything's going to cancel. What I'm going to do is maybe rewrite this negative 1 as just like a negative e to the negative x. Okay, at least that looks a little bit cleaner, but my point here is to take a moment to see, does anything simplify at all? And here I don't think it does. So we'll just go ahead and apply L'Hopital's rule. The derivative of 2x is 2. In the denominator, that negative is going to hang out. When I differentiate e to the negative x, I get e to the negative x times the derivative of the inside stuff. So in the denominator, I have a double negative, so they will cancel. So we just have 2 over e to the opposite of x. And now when I try direct substitution, I just have a fixed 2 in the top. And in the bottom, that's going to be like an e to the infinity. 2 over infinity is going to go to 0. So the limit as x approaches negative infinity of x squared over e to the negative x is equal to 0. All right, so in that one, we ended up using L'Hopital's rule more than one time. That can happen. All right, let's look at another example. This one, so what's different about this one is that when I look at it, I don't see a fraction. So if I were to check it, maybe I'd get an indeterminate form, but there's no way that I can use L'Hopital's rule here. It's not possible if it's not a fraction, because L'Hopital's rule is designed for a fraction. So what we could do is we could say, well, what if I rearrange this first before I do anything else? Let's try and force there to be a fraction here. And in this case, I think that it's not too big a stretch because I have this negative exponent, and I can always rewrite a negative exponent as going in the denominator as a positive exponent. So before I do anything else, I'm not using L'Hopital's rule or anything. I'm just going to rewrite this as the square root of x over e to the x. Now at least I have a fraction. So I'm going to try direct substitution and see what I get. So in the numerator, I have the square root of infinity, and the denominator, I have e to the infinity. If I take a number that's going towards infinity and square root it, that's still a big number. E to a big number is an even bigger number, so we have an infinity over infinity case, so we can use L'Hopital's rule. What I might want to do before I use L'Hopital's rule, it's not necessary, but it could be helpful. I'm going to rewrite that square root as a half power so that it's, I don't accidentally make any mistakes when I differentiate here. So using L'Hopital's rule, I get the limit as x goes to infinity, differentiate the top 1/2 x to the negative half power, differentiate the bottom, the derivative of e to the x is e to the x. Now, you can plug in here, but I always find it helpful before and after L'Hopital's rule, all the time, to simplify. And I don't really like negative exponents because they're confusing. So I'm going to take this x to a negative power and put it in the denominator as an x to a positive power. Okay, so I'm just going to rewrite things a little bit. So this x to a negative half, I can put in the denominator as an x to a positive half, or I can even rewrite it as a root x. Same thing with a 1/2. 1/2 in the numerator is like a 2 in the denominator, and the e to the x we'll leave alone. So I don't have anything left in the numerator, just a factor of 1. So now let's try direct substitution. And what I get is 1 over 2 times infinity. That's a 1 over infinity, which gives me 0. So the limit as x goes to infinity, e to the negative x root x is equal to 0. Okay. Now, again, I want to emphasize 1 over infinity equals 0 doesn't make sense. Infinity is not a number. We can't divide by a number, right? I can't take a number divided by something that's not a number. and then get a number, right? That's not what we're doing here. We're not doing arithmetic. What we're doing is we're saying, okay, in a limit, as I take a quantity that's going to infinity and divide by it, then the whole fraction is going towards 0. Don't allow your brain to get too sloppy and think of infinity as a number that you can do arithmetic with. All right, let's try another example. I'm going to show you something different with this one. So I'm going to take the limit as x goes to pi of sine x over 1 minus cosine x. And I'm going to warn you ahead of time that I'm going to make a giant mistake. Okay, so this is what I'm about to write is incorrect. I'm going to say that this is equal to the limit as x goes to pi. Apply L'Hopital's rule. The derivative of sine x is cosine x. The derivative of, on the bottom, the derivative of 1 is 0. The derivative of, so I have 0 minus, the derivative of cosine x is negative sine x. So that's tricky because I have this double negative, but I didn't make a mistake there. So my double negative gives me a positive sine x, so 0 plus sine x is just a sine x in the denominator. Oh, I probably should have made this a one-sided limit. Let's back it up and say this is approaching from the left. That won't become necessary when we do this correctly, but it is necessary for this part. All right, cosine x over sine x. When I plug in infinity for cosine, cosine of infinity is like a -1. And when I plug in something approaching pi into sine, sine of pi is 0. As I approach from the left, though, if I think of plugging in angles that are slightly smaller than pi, I will get a positive number. So this is going to be close to 0, but positive. You know, like a 1 over 0 is going to go to infinity. I have a negative in here, so this is negative infinity. It was only in this very first step that I made a mistake. And my mistake was that I used L'Hopital's rule. Not that I used it incorrectly. It's that I used it at all. If I went back to my original function and tried direct substitution here, I would get sine of pi over 1 minus cosine of pi. The sine of pi is 0. Cosine of pi is -1. 1 minus -1 is 2. 0 divided by 2 is 0. This is not 0 over 0, and this is not infinity over infinity. So we can't use L'Hopital's rule. And in fact, I don't need to. We have the answer. It's just 0. When I use L'Hopital's rule, I get a wrong answer because I wasn't allowed to use L'Hopital's rule. So if I use L'Hopital's rule when I'm not allowed to, I'm going to get a wrong answer. So this is why it's really important to always check that condition. Do we have a 0 over 0 or an infinity over infinity? So the limit as x goes to pi from the left, and it'd be the same from the right, of sine of x over 1 minus cosine of x is equal to 0. If you use L'Hopital's rule, you get negative infinity, and that's incorrect. Okay, again, always double check. Make sure that you're allowed to use it first. Here, we'll do another example like that where we're not allowed to use L'Hopital's rule, but maybe it'll be more, you know, I want to show you it doesn't just happen with like trig functions. So let's look at the limit as x approaches -1 of x squared minus x minus 6 over x squared plus 3x plus 2. So let's incorrectly apply L'Hopital's rule. And I get the limit as x approaches -1, 2x minus 1 on top, 2x plus 3 on bottom. And now I plug in. Two times -1 is -2, minus 1 is -3. -2 plus 3 is +1. So we just end up with -3. Okay, and that's incorrect. If I tried direct substitution right away, I would get -1 squared minus -1 minus 6 on top, -1 squared plus 3 times -1 plus 2 in the denominator. So we get 1 plus 1 minus 6 over 1 minus 3 plus 2. which is negative 4 over 0, which tells me I have an infinite limit. So I know that this is either going to be infinity or negative infinity, or it's going to split and just not exist, right? If it goes to 1 on one side and the other on the other side. Okay, so I know that this negative 3 is definitely not correct. When I have an infinite limit, I'm going to treat this just like I did with other infinite limit problems that we had back in Chapter 2. I'm not going to use any L'Hopital's rule stuff because it's not the right form. Okay, so I could look at this from the left and the right and see if they match and do something like that. Just to make things a little bit easier, I'm going to go ahead and factor this. So the numerator will factor into an x plus 2 times an x minus 3. And the denominator will factor into x plus 2, x plus 1. We can cancel the x minus 2's, but the x plus 2's, but the x plus 2 isn't the factor that's giving us a problem. That's not where the 0 in the denominator comes from. Okay, so I'm going to now look at this from the left and the right. Say the limit as x approaches negative 1 from the left. If I put in something close to negative 1 and subtract 3, I've got something close to negative 4. That's definitely a negative. Right, when I put in negative 1 plus 1, I know it's about 0. But if I'm approaching from the left, or slightly to the left of, or more negative than negative 1, so when I add 1, it's still going to be negative. So we're going to get positive infinity there. If I look at the limit as x approaches negative 1 from the right, x minus 3 over x plus 1. Okay, once again, something close to negative 1 minus 3 is going to be about negative 4. That's a negative. Here, if I approach negative 1 from the right, it's close to negative 1. So when I add 1, it's close to 0. But if I'm to the right of negative 1, when I add 1, we'll have a positive. Okay. So the limit as x approaches negative 1, because these two don't match, the limit doesn't exist. Okay. And again, what I wanted to emphasize here was that we have to be careful and check and see if L'Hopital's rule applies. All right, let's go through another example. L'Hopital's rule will work on this one, but not right away. Let's look at the limit as x goes to infinity of 1 plus 1 over x to the power of x. This is, I mean, there's a fraction in here, but this is not a fraction. So I know ahead of time L'Hopital's rule is not going to work. We can try direct substitution, though, just to see what happens. If I try direct substitution, as x goes to infinity, I know 1 over x is going to 0. And this x over here is going to infinity. So I have a 1 to infinity power. And just in case you're not sure, we can go back and look. And that 1 to infinity is indeed one of our indeterminate forms. Okay, so we don't know what's happening here. So we can't just say this is what it is. It's not just 1. It's not infinity. It could be anything. So we don't know the value of the limit, but we don't have the right form for L'Hopital's rule. Feels like we're kind of stuck. Problem, the thing that's making us stuck is this exponent, right? This power of x is really cramping our style over here. And in the past, when we had a troublesome exponent, we said, well, let's use logs to get rid of it. But I don't have an equation here, so I can't just take log on both sides. So I'm going to make an equation. I'm going to say, let y equal the limit as x goes to infinity of 1 plus 1 over x to the power of x. All I did was give a name to this limit. I'm just going to call it y, so I'm just looking for y now. But now it looks like I have an equation, so I can do things that we can do to equations, like take the natural log of both sides. So then I have natural log of y equals the limit as x goes to infinity of the natural log of 1 plus 1 over x to the power of x. And remember, the property of natural logs that is so useful here is that when you have natural log of stuff to a power, you can bring that power out front, in front of the natural log as a coefficient. So natural log of y is going to equal the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. Now, it's very important here that you remember that we are not doing a derivative problem. What we're doing is we're trying to make our limit look like a L'Hopital rule problem so that we can apply L'Hopital's rule, because we don't really have another thing that will work nicely here. So what I want to do is create a fraction. And I know you see the 1 over x, that is a fraction, but it's added to 1 and it's inside a log, and I can't really write this whole thing as one big numerator and denominator. So what I'm going to do is I'm going to force this multiplication to be division instead, by taking one of these things and putting it in the denominator in a way that's equivalent. So the way that I can do that is if I have an x here, say to the power of 1, I can put it in the denominator as an x to the negative 1, or like a 1 over x. I'll just make a side note. X is equal to 1 divided by 1 over x, which is 1 over x to the negative 1 power. Now we're used to going the other direction. If you had 1 over x to the negative 1 power, you could simplify that to being x. Similarly, if I had a 1 over x in the denominator, I could, simplify that to give me just an x in the numerator, or like an x over 1. What we're doing is we're going backwards. We're taking something that's already simplified and we're making it more complicated in a sense, because we really want to have that fraction. This is a weird phenomenon. Never in algebra did you say to yourself, there's no fraction here. Let's try to get one in here. Okay, so let's see what happens. I'm going to have this ln of 1 plus, I'm going to rewrite this as let's leave it as a 1 over x for now. I have natural log of 1 plus 1 over x in the numerator, and a 1 over x in the denominator. And now I'm going to try direct substitution and see what happens. Is this the right form for L'Hopital's rule? And am I allowed to, use L'Hopital's rule? Do I need it? Can I solve it without it? So let's see what happens. As x goes to infinity, 1 over x goes to 0. So this is going to look like natural log of 1 plus 0 over 0. 1 plus 0 is 1, and natural log of 1 is 0. So I have a 0 over 0 situation. So we can use L'Hopital's rule. Okay, I'm not going to use L'Hopital's rule yet. I am going to do one more step. I'm going to rewrite this as the limit as x goes to infinity of natural log of 1 plus x to the negative 1 all over x to the negative 1. Don't have to do that. But just like I said before, I prefer to write it as a negative exponent so that I can clearly see that I'm doing a power rule when I differentiate it. Okay, so now let's use L'Hopital's rule. All right, in the numerator, I have to do a chain rule. The derivative of natural log of stuff is 1 over that inside stuff times the derivative of the inside stuff. The derivative of 1 is 0. The derivative of x to the negative 1 is negative x to the negative 2. And the denominator, when I differentiate x to the negative 1, I get negative x to the negative 2. Okay, before I do anything else, let's simplify. Okay, always simplify, before and after L'Hopital's rule. 0 plus something is just that something. So I have a negative x to the negative 2 over 1 plus x to the negative 1. And then I have a negative x to the negative 2 in the denominator here. I don't like having multiple layers of fractions. So what I'm going to do is I'm going to take this negative x to the negative 2 in the denominator and move it up to the numerator as an x to a positive power. So I have negative x to the negative 2 over 1 plus x to the negative 1 times negative x to the positive 2. Okay, well, I might as well combine that with the numerator that I already have. Negative times a negative is a positive. X to the negative 2 times x to the positive 2 is 1. Now try direct substitution. So I'm not really doing direct substitution here. I'm really actually using my theorem from 4.5 when we said if I have a 1 over x, that's what this x to the negative 1 is. As x goes to infinity, 1 over x goes to 0. So it might be easier to see if I write this as the limit as x goes to infinity of 1 over 1 plus 1 over x. And then I say, okay, that's 1 over 1 plus 0, which is just 1. What I need to be very careful about, and this is a great problem to illustrate why it's important that we're careful and deliberate when we're doing a problem. I'm going to follow my chain of equals, right? This thing is equal to 1. that's equal to this thing, which is this thing, which is equal to this thing. And if I follow it back up, I say that's equal to natural log of y. My original limit was equal to y. Okay, so natural log of y is equal to 1. That tells me that y is equal to e to the 1, which is just e. So my original limit isn't equal to 1, it's equal to e. All right, that's one of the more complicated L'Hopital rule problems. Let's try. I feel like we can't end having just one of these really complicated ones. So let's go through 2 more just so that we see a big enough variety of complicated L'Hopital rule examples. So let's look at the limit as x goes to 0 of tangent x minus x over x cubed. We're actually not going to need a logarithm in this one at all, but I feel like this is still a complicated one. I know that this is often confusing. So let's just go ahead and see what happens with this one. I'm going to start by trying direct substitution, like normal. So I have tangent of 0 minus 0 over 0 cubed. Tangent of 0 is 0. So we have 0 over 0, so we can use L'Hopital's rule. This is equal to the limit as x goes to 0 of this new fraction. In the numerator, the derivative of tangent of x is secant squared x. The derivative of minus x is minus 1. In the denominator, the derivative of x cubed is 3x squared. I don't see any simplifying that I can do. So let's try L'Hopital's, or let's try direct substitution rather. Let's try direct substitution again. So I have secant squared of 0 minus 1 over 3 times 0 squared. Secant of 0 is 1. 1 squared is 1, minus 1 is 0. So we have 0 over 0 again. So use L'Hopital's rule again. Before I use L'Hopital's rule, I'm going to rewrite this as secant x squared. This is an easy place to make a mistake. If I write it as secant of x squared, then I can see how to differentiate using the chain rule. So now I'm going to differentiate using L'Hopital's rule. When I differentiate secant of x squared, my outside function is stuff squared. So I get 2 times the inside function, which is secant x, to the power of 1. I won't write the 1. And then times the derivative of the inside stuff. The derivative of secant x is secant x times tangent x. The derivative of minus 1 is 0. So that's the derivative of the numerator. Now in the denominator, 3x squared, when I differentiate, I'm going to get 6x, right? The 2 comes down, and I lower the power by 1. If I try direct substitution here, I'm going to get 0 over 0 again. But I'm going to do some simplifying first. I'm going to rewrite this. Secant of x times secant of x is secant squared x. And then I'm going to write the tangent of x over x sort of separately. Right? So I still have a 6x in the denominator. I have 2 secant squared x times tangent x in the numerator. This one, though, I think is going to be a little bit simpler, though, if I break these up. If I remember my properties of logs, if I have 2 multiplied logs, I can break them up into 2 separate set of limits. If I have the limit of 2 multiplied pieces, I can break this up into the product of 2 different limits. So I'm going to write this as the limit as x goes to 0 of 2 secant squared x over 6 times the limit as x goes to 0 of tangent of x over x. And the reason I'm going to do that is because I think that these are going to be easier pieces to work with. If I were to just look at this limit and say, I can do L'Hopital's rule, I get a very complicated derivative here because I get a product rule. One of my products has a chain rule with this crazy secant stuff inside, and the other one's a trig function. So it's really easy to make a mistake, and it definitely gets very big and complicated. You can work it out, but if I do this, it's going to be a lot simpler. Okay, let me work out these two limits separately. If I take the limit as x goes to 0 of tangent of x over x, if I'm really slick and I remember everything that we did back in chapter 3 with derivatives and particularly with trig functions, I could break this up into sine x over x and apply my one of the rules that I know. Let's just assume we forget that and say if I try direct substitution, I get tangent of 0 over 0, which is 0 over 0. So we use L'Hopital's rule. So the derivative of tangent x is secant squared x, and the derivative of x is 1. So I get secant squared of 0 over 1, and secant of 0 is 1. So this is just 1. So coming back here, I have 2 times secant squared of 0 over 6 times 1. Secant of 0 is 1, so I get 2 over 6 times 1 times 1, and 2 sixths, a third. Okay. So our limit, the original limit, is equal to 1/3. All right, this one, I don't know that I can point to exactly what makes this one tricky, but like it just has a lot of steps to it, right? There's 3 layers of L'Hopital's rule, and we have to be careful with simplifying, and of course there's trig functions. So I don't know that there's like any one trick there. It's just a complicated problem. Okay. So we'll do one last example. Okay, so let's look at this. The limit as x goes to infinity of x over x plus 1, all raised to the power of x. And again, I can see this exponent is going to give me trouble. So I don't even need to try direct substitution first, because I know there's like nothing I can do here. If I do try direct substitution, just to make sure that I get an indeterminate form, I get infinity over infinity plus 1 to the infinity. And like I'm kind of stuck even at the beginning, because infinity over infinity could be anything. So like, do I have a 0 to infinity or a 1 to the infinity or an infinity to the infinity? I don't even know. So this one is just even more complicated than the indeterminate forms that we've written down. So we don't really know where to go here. And it's this exponent, again, that gives us an issue. So we need to get rid of the exponent, and the only way to deal with it is with a logarithm. So we're going to let y equal this limit so that we can take the natural log of both sides. So the natural log of y is equal to the limit as x goes to infinity of the natural log of x over x plus 1 dx, and we use our property of logs to bring that x down out front. Okay, and I'm going to do the same trick that we had before. I need to make a fraction, so I'm going to take this x and move it into the denominator as an x to the negative 1 power. So we have natural log of x over x plus 1 all over x to the negative 1 power. Now I have a fraction. So now let's try direct substitution and see what happens. When I try direct substitution, we have natural log of x over x plus, oops, I don't want x's here. We're plugging in, so we have like an infinity. I can say, well, this is, again, problematic because I don't know what's going on with this inside. I have an infinity over infinity. If I'm a little bit more careful with it, if I just say, what happens as x goes to infinity of x over x plus 1, what I could do is apply one of my strategies from back in section 4.5 and say, well, I have a fraction, I have x going to infinity, divide by the biggest power of x in the denominator. So when I divide by x, I'll get 1 over 1 plus 1 over x. And as x goes to infinity, that's going to give me 1 over 1 plus 0, which is 1 over 1, which is 1. So instead of writing an infinity over infinity plus 1, I can say that's like a natural log of 1 now. So in the numerator, I have natural log of 1, which is 0. In the bottom, I have 1 over infinity, which is 0. So we can use L'Hopital's rule. All right, we need to be very careful about this because our numerator is complicated. So I'm using L'Hopital's rule. In the numerator, when I take the natural log of stuff and I differentiate it, I'm going to get 1 over that inside stuff times the derivative of the inside stuff. Okay, in the denominator, when I differentiate x to the negative 1, I get negative x to the negative 2. Okay, so what I'm going to do is off to the side, I'm going to say, what is the derivative of x over x plus 1? I'm going to use the quotient rule. So the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Let's simplify. So multiplying by 1 doesn't change anything. So I have x plus 1 minus x all over x plus 1 squared. So this is just 1 over x plus 1 squared. Okay, so let's plug that in. So I have 1 divided by x over x plus 1 times 1 over x plus 1 squared in the numerator, and a negative x to the negative 2 in the denominator. So dividing by a fraction is the same as multiplying by its reciprocal. So I can rewrite this as x plus 1 over x. And likewise, taking this negative x to the negative 2 in the denominator, I can put it up as a negative x to the positive 2 in the numerator. Okay, so we can get rid of all of these multiple layer fractions. Okay, so combining things together, I have x plus 1 factor, 1, and a negative x squared factor in the numerator. We have an x times x plus 1 squared in the denominator. My x in the denominator will cancel with one of my x's. My x plus 1 factor in the numerator will cancel with one of my x plus 1 factors in the denominator. So I'm left with a negative x in the numerator, x plus 1 in the denominator. And it's your call whether or not you want to test this and say, okay, I can use the L'Hopital's rule. Or if you want to use the strategy that we had from 4.5, where we say as x is going to infinity, I can divide by the biggest power of x in the denominator. Either way works. Last time, up here, I divided by x. This time, I'll show you, hey, we can use L'Hopital's rule here. So the derivative of negative x is negative 1. The derivative of x plus 1 is 1 plus 0. So I get negative 1 over 1. Okay. Again, I'm going to follow backwards. What is this negative 1 equal to, right? Follow my chain of equality. Back up. It's equal to natural log of y. Since natural log of y is equal to negative 1, if I take e to the power of both sides, then y is equal to e to the negative 1, which is 1 over e. So the limit as x goes to infinity, this thing that we started with, x over x plus 1 to the x, is equal to 1 over e. Okay, that's our examples. I think that's good for L'Hopital's rule.